Today we're going to continue our series on equilibrium basics. We're going to start out with a few quiz-kin questions, and then we're going to talk about something called Le Chatelier's principle, which we've been introduced to before in the solids and liquids videos, but we'll look at it as it applies to other kinds of equilibria in today's video. And then I'm going to conclude with a few sample calculations that introduces something called a Rice chart that can be very useful in solving all kinds of equilibrium problems. Starting out with this quiz-kin question, we have calcium carbonate, which is a solid, decomposing to solid calcium oxide and carbon dioxide gas. And we have this data: when a mole of calcium carbonate reacts at 700 degrees C, the pressure at equilibrium is 0.105 atmospheres. And the question is, first of all, what is Kp for this reaction? And then the second question is, what is Kc for the reaction? Well, let's solve this problem. Let's start out by giving ourselves a balanced chemical equation. CaCO3 solid says is decomposing into CaO, which is a solid, and CO2 gas. And since this is an equilibrium problem, we can assume that this is a reversible reaction. The first question that we're asked to solve is, what is Kp? Well, Kp for this reaction is just defined as the pressure of all gases raised to their coefficients in the product side divided by the pressure of gases on the reactant side raised to their coefficients. And for this reaction, that just turns out to be the pressure of CO2. In numerical terms, it said that the pressure at equilibrium is 0.105 atmospheres, so Kp is 0.105. Now, I'm not going to put any units here, and I shouldn't. We've been developing the idea of equilibrium constant from a stoichiometry and concentration perspective. But originally, these ideas were developed from a thermodynamics standpoint, and they were developed without units, and so we should not put units on values of K. The second question is asking, what is Kc? Here's a relationship that we have. We know that Kp is equal to Kc times R times T raised to the change in number of moles of gas. So if we want Kc, we can solve for it. Kc would be equal to Kp divided by R times T raised to the change in number of moles of gas. So Kp, we'll put in 0.105. We've already solved for that. R, well, the R that we're going to use here is the 0.0821 liter atmospheres per mole, Kelvin R. And I'm not going to put units on it because it's going to be unitless in the end anyway. However, that is in terms of absolute temperature, and so instead of 700 Celsius, I'm going to put 973 kelvins in here. And then this is supposed to be raised to the change in number of moles of gas. Well, what is that? If I look at my balanced equation, I have 1 mole of gas on the right. That's a solid, and that's a solid, so no moles of gas on the left. So my change in number of moles of gas is 1 mole minus 0, or just 1. So I'll be raising the denominator to the 1 power here. When I do my arithmetic, I come up with 0.00131 for a value of Kc. So just to summarize, Kp is 0.105, Kc is 0.00131. Here's the next quiz-kin question. It says at 25 degrees C, Kc is 2.2 times 10 to the minus third for 1 ICl gas decomposing to 1/2 I2 and 1/2 Cl2 gas. We're supposed to find Kc at the same temperature for 2 ICl decomposing to 1 I2 and 2 Cl2s. Stop the video and give this a try, and I'll bring you an answer and then a solution. Well, what's happened here is we've doubled the coefficients. And what we learned about doubling coefficients is you have to take the K value and then raise it to whatever you've done to the coefficients. So doubling the coefficients means we should square the value of Kc. So Kc for the new reaction here should be equal to 2.2 times 10 to the minus third squared, which works out to 4.8 times 10 to the negative 6th. The next question asks us for the Kc when 2I2 and 2Cl2 are in equilibrium with 4ICl. Stop the video and see if you can come up with an answer, and I'll bring you a solution and an answer. Well, two things have happened here. One is that the reaction is reversed. When the reaction is reversed, we have to take the reciprocal of the K value. So that would be 1 over Kc original, which is 2.2 times 10 to the negative third. But a second thing is going on here. The coefficients have gone from 1/2 in the original equation for the I and the Cl2 up to 2. And the original ICl coefficient was 1, and it's now 4. So that means we've multiplied the coefficients by 4. That means we need to raise the K value to the 4th power. So this is 1 over 2.2 times 10 to the minus third raised to the 4th power, because the coefficients have been quadrupled. The reciprocal is taken because, remember, we flipped the reaction around. So when you do all this arithmetic, you come up with 4.3 times 10 to the 10th. Our third question is asking us this. You have 700 degrees C, you have 2 Kc values given for 2 reactions, and you're supposed to find Kc for a third reaction at the same temperature. Stop the video and see if you can figure out how to do this. I'll give you an answer and a solution momentarily. Well, here are the original reactions reproduced here, and our target reaction is SO2 gas plus NO2 gas in equilibrium with NO gas and SO3 gas. So using this top equation here, I can see that I can leave it in the same direction that it's going, but I need to change the coefficients. I need to reduce them by half. So I'm going to take the first equation here and rewrite it as 1 SO2 gas plus 1/2 O2 gas in equilibrium with 1 SO3 gas. Since I've divided the coefficients by 2, I need to take the square root of the Kc value. So Kc for this reaction, as I've written it, is going to be the square root of 400, which is just 20. The second equation is going to have to be flipped around so that I can get a mole of NO2 on the left-hand side. So changing this one, I'm going to go NO2 gas in equilibrium with NO gas and 1/2 O2 gas. Because I've reversed it, K for the new reaction is 1 over the original K, so 1 over 2.22, which works out to 0.450. Now when I sum these two reactions up, 1/2 O2 gas cancels out from both sides, and I will get my target equation, SO2 gas plus NO2 gas in equilibrium with SO3 gas and NO gas. So since I added these two equations together and got my third equation, the law of multiple equilibria says the K for this equation is going to be equal to the Kc for the first equation times the Kc for the second equation. So Kc1, Kc2, I could say here, is going to give me Kc3. So putting numbers to that, Kc for this third reaction, the sum of the two previous reactions, is going to be 20.0 times 0.450. And that comes out to 9.01. Now let's talk about Le Chatelier's principle. Le Chatelier's principle in general says this: if a system at equilibrium is subjected to a stress, and we're going to talk about what that means in a little bit, the reaction shifts in a direction that will tend to relieve the stress that got placed on the system. So what are some stresses? One stress is the stress of changing concentrations. So let's investigate this by looking at an example. What would happen to the system if HI was added to this reaction system here, where 2HI is decomposing to H2 and I2? We add more HI. Well, let's analyze in detail what happens to the mass action expression and then see how the system would have to respond to attempt to go back to what it used to be before the stress was applied. Well, here's our original equation, and the Kc value here is 0.16, and Kc is equal to, in terms of concentrations, concentration of H2 times concentration of I2, because those are our two products, raised to the 1s, because those are their coefficients, divided by concentration of Hi squared, because the coefficient on Hi is 2. Well, this is a reaction that we originally investigated in the last video, and I'm going to take one of those experiments and use the equilibrium values that we know existed under certain conditions where 0.16 was the Kc value. So let's say 0.03 times 0.03 for H2 and I2 concentrations divided by 0.240 squared is equal to Kc. Those are the concentrations of those species at equilibrium. Let's say we add Hi until concentration of Hi is some higher value than the equilibrium concentration. Let's say 0.3. So it was at equilibrium 0.240, and now it's gone up to 0.3. Now let's reevaluate the mass action expression, which isn't at equilibrium anymore. It's Q, the reaction quotient, or mass action expression. So now we've got 0.03 times 0.03. We didn't add or take away any H2 or I2. And now we're dividing not by 0.240, but by 0.300 squared. This works out to 0.010. Now this system is only at equilibrium if Kc is Q, if Q works out to 0.16. Obviously, this number is too small. So what could you do to make a number larger? Well, one way you could make a number larger is make the numerator bigger. Another way you could make the number larger is to make the denominator smaller. And if you think about this reaction system, what's going to work to make the denominator smaller is to get rid of reactant. And that will also make the numerator larger because you'll get more product, and products are on top, reactants are on bottom. So how does the system respond? In order to attempt to get back to 0.16, which is equilibrium again, it's going to shift to the right to use up the additional Hi and produce more H2 and I2. In terms of a chart, here's time versus concentrations. Starting from whatever value, the Hi concentration dropped down to its equilibrium value of 0.240. Starting perhaps from 0, the concentrations of H2 and I2 rose until they were at 0.03. So at that point, we had established an equilibrium, and Kc was Q. Then we shifted things up. We suddenly increased the concentration of Hi up to 0.300. How did the system respond? Well, this is going to go back to equilibrium. So it drops, this value drops down again to some final equilibrium value. If the concentration of Hi went down, then the concentrations of H2 and I2 are going to have to respond by going up until a new equilibrium is established again and the concentrations are no longer changing. So when equilibrium gets reestablished, here's what you have. You're back to 0.16. The concentrations of H2 and I2 would have had to go up, and they end up going up to 0.08. They'll be the same because of the stoichiometry. And the concentration of Hi is going to have to drop from its original value, and it ends up being 0.20. Later on, I'll show you how you can make a prediction like that, but you've seen what happens here is the reaction had to shift from the right to the left to use up the additional reactant. Now let's ask ourselves, what would happen if a product is removed from the system? So in this case, H2 is removed from the system. Well, if it's at equilibrium, Kc is equal to concentration of H2 times concentration of I2 over concentration of Hi squared, and that all works out to the K value, 0.16, under the conditions that we had earlier. I've now removed from H2, so the concentration of H2 drops from what it originally was. This means that the mass action expression is no longer Kc. Just like we saw when we added extra reactant, the Q value is too small. How do you get the Q value back up to Kc? Well, you're going to have to make the numerator bigger by making more product, and you're going to have to make the denominator smaller by making less reactant. So just like we saw in the last example, this is going to predict a reaction shift to the right. So we could summarize this by saying adding reactant or removing product causes the reaction to shift to the right. Now let's look at this situation. What would happen if we added a product to the system below? So same reaction. Let's look again at Kc. Here's the Kc expression. It's H2 concentration times I2 concentration divided by concentration of Hi squared. This stress is increasing the concentration of H2. And this could be I2 as well, either product. It's going to respond the same way. What has happened to the value of Q? Well, Q is now bigger than Kc because the numerator's gotten larger and everything else has stayed the same. How can I make Q smaller and make it go back to Kc again? Well, the only way you can make a fraction smaller is by decreasing the size of the numerator or increasing the size of the denominator. And if I use up product and create more reactant, I'll do that. So this predicts a shift to the left in this reaction, using up the additional H2 and some I2 and creating more Hi until Q goes back to Kc. Let's look at another situation. What would happen if I took Hi and took it out of the system some way? Again, let's evaluate this in terms of what happens to the mass action expression. Kc is concentration of H2 times concentration of I2 divided by concentration of Hi squared. If I make this number go down, if I take Hi out of the system, the denominator gets smaller. That makes the number bigger. So just like in the last example, Q is larger than Kc. The only way I can make Q go back down to Kc is make the numerator larger and or make the denominator smaller. So we can generalize here and say that adding product or removing reactant will cause the reaction to shift to the left. Here we have two test tubes. One has got a copper chlorine complex that's green, and the other one has a copper water complex that's blue in color. We're going to have an experiment test tube here where we'll do some changes, and we'll keep those there for reference. This is a bottle of copper 2 sulfate, and I'm going to take this solution and pour it into our experiment test tube. When you do, you can clearly see that the copper water complex is present because it's the same color as the test tube that's on the right. Comparing the colors, you can see that they are nearly identical. Now I'm going to take a bottle of hydrochloric acid, which is a source of chloride ions because it's a strong electrolyte. As I pour the chloride ions in solution, I see a slight change in color because I've established this equilibrium between the two complexes. The color is slightly different, but still quite blue. As I add even more hydrochloric acid, the excess of chloride ion causes the shift to the right, producing more of the green copper chlorine complex. And if we inspect the test tubes, we can see that it's much closer to the test tube on the left now. I've poured out a little bit of my solution to reduce the volume, and now I'm going to take a bottle of water and add some water to the test tube. As I add water, we should see an equilibrium shift from the right to the left, indicating that water would be used up and more of the blue copper water complex is formed. After I stir it up and we compare colors, we can see that again it is much more like the original color. Here's another stress, and that is changing volume. Now this only affects gaseous equilibria, but let's take a look at what would be predicted. What would happen to this system here if the volume were decreased, the overall volume? here's our equilibrium. These are all gases, and so we can think about this in terms of Kp. Kp is equal to the partial pressure of SO3 squared divided by the partial pressure of SO2 squared times the partial pressure of oxygen to the 1 power. Now let's change this expression so we get volume in here. P is equal to nRT divided by V, so let's just exchange all these pressures for number of moles. So N SO3 times R times T divided by V squared is in the numerator, and the denominator is number of moles of SO2 times R times T over V squared times number of moles of oxygen times R times T over V to the 1 power. So we can factor out an RT over V here, and we get this. Kp is really equal to number of moles of SO3 squared over number of moles of SO2 squared times number of moles of O2 to the 1 power times RT over V to the 2 minus 3, which is to the -1. Well, something raised to the -1 means just its reciprocal, so this changes to number of moles of SO3 squared over number of moles of SO2 squared times number of moles of O2 to the 1 times V over R times T. Now what happens if we make the volume smaller? So now I've decreased the size of the volume. Q is now less than Kp because I decreased the size of the numerator and the denominator stayed the same. How do I get back to Kp? Well, the only thing I can do is to decrease the denominator and increase the numerator. So that means I'm going to have the concentrations of my products go up and the concentration of my reactant go down. So I'm going to see a shift from left to right, produce more product. Now here's how we can generalize that. On the left-hand side I have 3 moles of gas. On the right-hand side I have 2 moles of gas. Maybe a more satisfying explanation is I've reduced the amount of space that's available for gas particles. So the reaction is going to shift in a way that makes fewer gas particles because there's just less space for particles in the gas phase. So we could generalize by saying a decrease in volume causes the reaction to shift in the direction that reduces the number of moles of gas. So what would happen if the volume of the system were increased? Well, using the same kind of thinking, it shouldn't be too hard to imagine that if I have 2 moles here and I have 3 moles of gas on the left-hand side, and I increase the space available for gas particles, the pressure is going to drop initially. To get back to the equilibrium pressures, I want to produce more particles to fill that space back up and bring my pressure back up. So that would cause a shift to the left, to the direction that has more moles of gas. So an increase in volume will cause the reaction to shift in the direction that increases the number of moles of gas, whichever direction that happens to be. What you're seeing here is a syringe that has a little bit of liquid methanol in it, just a tiny drop of liquid methanol. And it's at equilibrium with methanol vapor because some of it has evaporated. Now watch what happens as I slowly decrease the volume. See it fogging up? Those are tiny droplets of liquid methanol. Liquid methanol is encouraged to form when the volume drops and the pressure increases because that reduces the number of moles of gas. When I reduce the pressure, it evaporates again. One more stress, and that is the stress of a temperature change. What would happen to the system down here that's at equilibrium if it were placed in a higher temperature environment? Now, we don't have information about K here. We don't really need it to make this decision. But we do have information about the delta H. Delta H is positive for this reaction. What that means is it's endothermic. So we could rewrite this a different way. We could say N2O4 gas plus heat is in equilibrium with NO2 gas. So what happens if I put it in a higher temperature environment? I'm increasing the amount of heat. Thinking about heat as a reactant, we can use our changing concentrations argument to figure out what will happen here. To get back to where we used to be, we have to use up the additional heat. That means the reaction is going to shift to the right. So now let's think about what would happen if that same system, were placed in a low temperature environment. Again, rewriting this as N2O4 gas plus heat in equilibrium with NO2 gas. And now thinking about the fact that now we have reduced the amount of heat present by putting it in a lower temperature environment, taking heat out of the system is going to cause a shift in the direction that undoes that stress. In other words, it's going to go to the left and create more heat to make up for the lost heat by going in a lower temperature environment. So we can generalize by saying an increase in temperature causes the reaction to shift in the endothermic direction. A decrease in temperature is going to cause the reaction to shift in the exothermic direction. Here we have two tubes that both contain the same equilibrium. It's N2O4, a light yellow gas, in equilibrium with NO2, which is a dark brown gas. The reaction is endothermic as it's written, so in a high temperature environment, we should see a shift to the right, producing the dark brown NO2. In a low temperature environment, we should see the lighter colored N2O4. After some time elapses, we'll remove the tube that's in the high temperature environment, and we find that, in fact, it has produced a large amount of the dark brown NO2. The other tube has produced the light yellow N2O4 predominantly. Let's reverse the tubes, put them back in opposite water baths, and see if we can get the reaction to shift the other way. According to Le Chatelier's principle, they should switch colors. After some time elapses, we find out that, in fact, the tube in the high temperature environment is dark brown, and the low temperature one is yellow. Here we have two spoons that have a special coating that has a colored dye that reacts with heat to produce a colorless dye. When we put it in a high temperature bath, it shifts to the colorless side and they appear white. When we put it in a cold water bath, it shifts back and we see the colored dye. And you can make this shift back and forth and back and forth over and over again. Now I'm going to introduce you to some tricks that we can use to solve equilibrium type problems by doing 3 example calculations. The first one here says I have 0.2 moles of H2, 0.2 moles of I2, and I'm putting them in a 2-liter flask and allowing them to reach equilibrium. Here's the relevant equilibrium expression, the reversible reaction. And we know that at equilibrium, I2 is going to be equal to 0.02 molar, and our job is to determine what is Kc for this reaction at this particular temperature. In general, here's what's going to happen. Look at this chart. Here's time, or reaction coordinate, and concentrations are on the y-axis. We know that our concentrations of H2 and I2 start out at 0.100, and there isn't any HI. So we've seen this before. What will happen is this concentration will drop. That's concentration of H2, concentration of I2. They'll drop. And the concentration of HI is going to rise until they reach some equilibrium value. So the question is, what are those values at equilibrium, and how do they relate to give us our Kc value? Let's think about what Kc is, first of all. The reaction, again, is H2 plus I2 in equilibrium with 2HI. The expression for the equilibrium constant is going to be equal to Kc equals concentration of HI squared divided by concentrations of H2 times concentration of I2. We just know that at equilibrium, the concentration of I2 is equal to 0.020 molar. That's all we know. And from there, we have to determine what Kc is. Well, all these things are stoichiometrically related. And so here's how we solve this kind of a problem. We use what's called the Rice chart. And here's what Rice stands for. Reaction initial, change, and equilibrium. And so you have this chart that has 4 lines. The first line has the reaction. The second line has what are the initial concentrations of all species present. In this particular reaction, it says that 0.2 moles of H2 and 0.2 moles of I2 are put in a 2-liter flask. So the concentration of H2 is equal to the concentration of I2, and that is equal to 0.200 moles per 2 liters. So that means we have an initial concentration of 0.100 molar. So our initial concentrations for H2 and I2 are 0.100 molar, and for HI we have nothing. What are the changes? Now here's where stoichiometry comes in. We know that this reaction is going to shift to the right. We're going to produce HI and use up H2 and I2. So we're going to lose some moles of H2 and we're going to lose some moles of I2. How much? The concentration of H2 and I2 are going to drop from 0.100 down to the equilibrium value of we don't know what. Well, it's a variable. It's an unknown. So let's call it X. So we're going to say that this value drops by X. Because of stoichiometry, we know every time we use up a mole of H2 or I2, we're going to create 2 moles of HI because the coefficient is 2. So if we lose X moles of H2 and I2, we are going to gain 2X moles of HI. So our concentrations when we reach equilibrium are this. At equilibrium in the E row, 0.100 minus X will be the concentration of H2. Concentration of I2 will also be 0.100 minus X. And the concentration of HI will be 2X. So what's Kc again? Well, Kc is going to be concentration of HI at equilibrium squared divided by the concentration of H2 times the concentration of I2 at equilibrium. In terms of our chart here, in the equilibrium line, we now know what concentrations of all these species are. Kc could be rewritten this way. It could be rewritten as 2X, that's the concentration of HI, squared, divided by 0.100 minus X to the 1 power, because that's concentration of H2, times 0.100 minus X to the 1 power, because that's the concentration of I2. All right, so this whole thing simplifies to 4X squared divided by 0.100 minus X squared, and that's equal to Kc. Now, if we knew what X was, we could evaluate for Kc. We sort of do know what X is, because the equilibrium concentration of I2 is given to us, and the equilibrium concentration of I2 is 0.100 minus X. So, if 0.100 minus X is equal to 0.020 molar, so this means X is equal to 0.100 minus 0.020 molar, and that equals 0.080 molar. So if that's X, then here's what Kc is. Kc is equal to 4 times that value, 0.080 squared, divided by 0.100 minus 0.080, and that quantity b squared. What's that equal? The value is 64. Let's look at another example. Here's an equilibrium expression. It's all gases. Carbon monoxide and water are at equilibrium with CO2 and H2. Kc is given as 4.06, and we know that 0.10 moles of CO and 0.10 moles of H2 are reaching equilibrium in a 1-liter reaction vessel. So we want to know what are the concentrations of all reactants and products at equilibrium, it should say. Well, let's make a race chart. First of all, reaction, that's the first line. So CO, gas, plus H2O, gas, in equilibrium with CO2, gas, and H2, gas. So there's our reaction. The next line of the rice chart is the initial concentrations value. Well, it says 0.1 mole of CO and 0.1 mole of H2O are put in a 1-liter vessel. So the concentration is 0.100 moles per 1 liter, or 0.100 molar for both reactant species. And there's no CO2 put in there, or no H2 that we know of, so those have to be zeros. What's the change? That's the next row in the Rice chart. Well, the change is given by the stoichiometry. This is a balanced chemical equation. The coefficients are all 1. So I know I'm going to shift to the right because I have to reach equilibrium, and it's not going to be a 0 value for Kc. So I'm going to lose some moles. I don't know how much, so I'll say X of CO. I will lose the same number of moles of H2O, so that's also a minus X. But I'm going to gain that number of moles of CO2 and of H2. So that when I reach equilibrium, that's the last line of my Rice chart, I will have a concentration of CO that's 0.100 minus X, and of H2O that's also 0.100 minus X, and CO2 and H2 are both going to be 0 plus X, which is just X. Kc is equal to concentration of CO2 times concentration of H2 divided by concentration of CO times concentration of H2O. But in terms of our chart, CO2 and H2 are both X's, and so X squared is my numerator. And concentration of CO and H2O are both 0.100 minus X, so 0.100 minus X squared is my denominator. And that's equal to 4.06, because that's what Kc is. It's my job to find out X, because if I know X, I can plug it into that bottom row, that E row in my Rice chart, and find concentrations of everything. So I can take the square root of both sides. So the square root of 4.06 is going to be equal to the square root of X squared over 0.100 minus X quantity squared. So the square root of 4.06 is 2.01. So that's equal to X over 0.100 minus X. So that means 2.01 times 0.100 minus X is equal to X. And if I distribute that, I get 2.201 minus 2.01 times X is equal to X, which means that 0.201 is equal to 3.01 times X. And if I divide both sides by 3.01, I find that X is equal to 0.0668. So my concentration of CO2 and my concentration of H2 are both 0.0668 moles per liter, because X was their equilibrium concentration. The concentration of CO and the concentration of water were equal to 0.100 minus X, or minus 0.0668, now that we know what X is. And those work out to 0.033 molar. So now we have the concentrations of all products and reactants at equilibrium. This problem says in air, the concentration of nitrogen is 0.033 molar, and the concentration of oxygen is 0.00810 molar. In atmospheric air, these are actual values at 25 degrees C. So there's a reaction that can occur between nitrogen and oxygen and produces nitrogen monoxide. The Kc for this value is very small, 4.8 times 10 to the negative third at 25 degrees C. And that's good, because a small K value means that the reaction doesn't happen very much, and we don't really want lots of poisonous NO being created from the gases that are in our atmosphere. But the question here is, what is the concentration of NO in our atmosphere naturally occurring from this reversible reaction? Again, I'm going to establish a Rice chart here. The reaction is equal to N2 gas plus O2 gas in equilibrium with 2 NO gas. And I know that Kc for this reaction is 4.8 times 10 to the negative 31. And my job is to figure out what is this concentration when I'm at equilibrium. The next line of my Rice chart is initial concentration. And it told us in the problem that 0.033 was the initial concentration of N2 molar, and O2 molarity is 0.00810 moles per liter. And we're going to assume that the reaction hasn't happened yet, so there's no NO. Here's the change. I'm losing X moles of N2. I will lose the same number of moles of O2. but I will gain twice as many moles of NO because the stoichiometry is 1 to 2. So at equilibrium, my nitrogen concentration will be 0.033 minus X. My oxygen concentration will be 0.00810 minus X. And my NO concentration will be 0 plus 2X, which is just 2X. So Kc is equal to concentration of NO squared divided by concentration of N2 to the 1 power times concentration of O2 to the 1 power. But in terms of our chart, that means 2X squared in the numerator, because that's concentration of NO at equilibrium, divided by 0.033 minus X to the 1 power times 0.00810 minus X to the 1 power for concentration of O2. And this is all equal to 4.8 times 10 to the negative 31st. So this is one equation with one unknown, and it's solvable. It turns out to be a quadratic equation, and those aren't so easy to solve. Now with the use of graphing calculators, it's quite a bit easier, but there's a simplification that can make this not a quadratic equation anymore, make it easier to solve. And here's the simplification. Looking at the exponent on my K value, I see that it's a very small number. So that means it's not going to go very far to the right. In other words, compared with the initial concentrations of reactants, the 0.033 for nitrogen and the 0.00810 for oxygen, X is going to be pretty little. We're not going to lose very much X compared with those original starting values. So we can rewrite this, and we can say that the 4.8 times 10 to the negative 31st is probably pretty close to 2x quantity squared over 0.033 times 0.00810, because we're going to assume that X is so small compared with 0.033 and 0.00810 that when you think about significant figures, you wouldn't even end up having to subtract it at all. Now here's why this simplifies things dramatically, because now we don't have that X term in our equation. We have an X squared term, but that's easy to deal with by just taking a square root. Watch what we can do now. 2x, the quantity squared, is equal to 4x squared. And if I multiply 0.033 times 0.00810, I get 2.7 times 10 to the negative 4th, and that is equal to 4.8 times 10 to the negative 31st. So, continuing my algebra here, 4x squared is equal to 4.8 times 10 to the minus 31st times 2.7 times 10 to the minus 4th, and that ends up being 1.3 times 10 to the negative 34th. So if I take the square root of both sides, I find that 2x is equal to 1.1 times 10 to the negative 17th. And what I'm trying to find is the concentration of NO at equilibrium, and that's equal to 2x. So I'm done here. The concentration of NO at equilibrium is equal to 1.1 times 10 to the minus 17th. Now, it's important to go back and take a look at whether our simplification that we did was a valid assumption or not. And in fact, if we look at what the value of x is, by dividing 1.1 times 10 to the minus 17th by 2, we end up getting 5.5. X is equal to 5.5 times 10 to the minus 18th. Now, if you take this number and compare it with 0.033, and you compare it with 0.00810, in fact, that number is so small compared with those initial concentrations that really X can be ignored. And so we were justified in doing that. Sometimes it's not quite as clear-cut as this. So we have a sort of a general guideline that we go by. If you make this simplification and you end up with an X that's less than 5% of the original concentration, you are justified in making that assumption. If it's more than 5% of the original concentration, well, then you actually somehow have to deal with the quadratic equation. There are two ways to do that. One is you can guess and check and just keep simplifying until you get the right answer. That's what we would have done in my day. But now that you have graphing calculators, it's probably much easier to just graph it out and find x. So these three example calculations really set the stage for all the kinds of examples that you'll have to solve in the remaining equilibrium studies that we'll encounter in upcoming videos.